So I want to get the x in the equation on the left by itself on one side of the equation. And when we talked about this last class, we came up with sort of three really important things that we can do to make a horrifying looking equation into a slightly less horrifying looking equation. Right? There are three things that were especially hairy about the equations we solved on Monday, and these were the three steps that we can take to make them less hairy. The first is that when my equation has a bunch of fractions in it, and this is the step that I like to do right out of the chute, let's get rid of the fractions by clearing out the denominators, which we accomplish by multiplying both sides of the equation by a common multiple of all the denominators that are present. So we'll get rid of all the fractions right off the top. Once the fractions are all gone and everything is whole numbers, the next hairy thing is that we might have variables on both sides of the equation. That x that we're trying to get by itself might reside both on the left and the right of the equal sign. And so that would be the next thing to take care of. Let's move all the variable terms onto one side of the equal sign, which is always something you accomplish by subtracting or adding a term, never something you accomplish by dividing. If I catch you dividing by a variable in a problem, dividing by x, you can be sure my purple pen is going to come out and have something to say about that. So moving terms from one side to the other, always an additive or a subtractive process. And once you're done with that, the variable will be only on one side of the equation, and we can finish unwrapping it, which we do by reversing the order of operations. Because that arithmetic and algebra which make that expression follow the order of operations forward. But the last thing that gets done has to be the first thing that we undo when we're unwrapping the variable. So we'll worry about additions and subtractions first when we're trying to get the variable by itself. Then after all that's done, we'll worry about multiplication and division. When all that's done, we'll worry about how to get rid of exponents. And we'll work from the outside of parentheses toward the inside of parentheses, which might be something that you saw happen, even if you weren't aware of it, when you solved the problem on the right. So let's follow this line of reasoning and take a look at our first problem. If I wanted to clear the denominators on both sides of this equation by multiplying, what's a good thing to multiply by? 10. So why is 10 a good choice to multiply on both sides of this equation, Darren? Yeah, exactly. We're looking for each of them, and you said them meaning what here? The denominators. So we looked at all the denominators that were present in the original equation, 5, 2, and 10, and asked, what's a number which is a multiple of all three of those? A multiple of 2, and a multiple of 5, and a multiple of 10. Well, there's a lot of numbers that do that. 100 is an example. 250 would be an example. But the smallest example is 10. And using the smallest example is going to give us the easiest arithmetic down the line. So 10 is a common multiple of 2, 5, and 10. And so let's use it. And the way I like to do this, because we know we're going to end up multiplying some fractions, let's make those 10s into 10 over 1s. Just right out of the chute on that one. And then when I multiply, let's take the fraction on the right here first. I'm going to multiply 10x minus 7 over 10, multiplied by 10 over 1. How do you multiply fractions again?
Straight across.
Straight across. So what I really ought to do is just go straight across those numerators and straight across those denominators. But rather than do that right away, I'm going to employ this little sleight of hand that we talked about also last time. And I'm first going to take the two denominators and just flip-flop them. Take this 10 and this 1 and just turn around. After all, 10 times 1 and 1 times 10 give us the same result. So it shouldn't matter which order we multiply them. So I'm just going to take those two denominators and flip-flop them. And what I end up multiplying instead then is 10x minus 7 over 1 times 10 over 10. And that's going to make my life easy because what's 10 over 10? 1. And 10x minus 7 divided by 1? Well, dividing by 1 is the same as not dividing by anything at all. And so when all of that dust settles, my right-hand side becomes just 10x minus 7, simply. So flip-flopping, trading places when I multiply fractions with the two denominators or with the two numerators, whatever is more useful, is a handy little trick. And I'm going to use that trick again when we multiply these fractions on the left-hand side. So on the left-hand side, if I'm going to multiply by 10 over 1, what do I end up actually multiplying inside this quantity? What did you do with the 10 that you had out front here? Okay, so it multiplied in here and it hit that x that was in the numerator of this fraction, and what else? It hits the 2. What else? It hits the 2x all the way over here. It hits the 1 all the way over here. So yeah, the first point is that I'm multiplying on the outside of a set of parentheses that has addition or subtraction happening on the inside. Right? If I zoom out and look at this, I've got one fraction minus another fraction inside the parentheses, and on the outside of those parentheses I have multiplication. So the distributive property of multiplication over addition, distribute multiplication over addition, tells us that we need to jump that 10 into all the terms that are on the inside of the parentheses. So that's the first. Sometimes if people forget these parentheses, they might accidentally not distribute the 10 to everything it needs to go to. So don't forget those parentheses. So if I just do that step, I'm looking at 10 over 1 multiplied by our first fraction, x minus 2 over 5. And then I'm going to have minus 10 over 1 multiplied by our second fraction, 2x plus 1 over 2. And I still have an equal sign in here. But to make that multiplication easier, I'm again going to flip-flop. Flip-flop my denominators, my 1's and my 2's, my 1's and my 5's. And again, the reason I like to flip-flop is it gets together the 10 with the number which 10 is going to be reduced by. So after I flip-flop my denominators, now my scary-looking algebraic binomials, x minus 2, 2x plus 1, those now have 1's underneath them as their denominators, which means we don't have to do anything. We can just leave them as they are. And the real arithmetic happens when we divide 10 by 5 and 10 by 2. So 10 divided by 5 is going to give me 2. 10 divided by 2 is going to give me 5. And then I've got x minus 2 from here, and I have 2x plus 1 from here. And then I've got an equal sign. I've got a minus going on in here. But I need one more thing on this line to complete my thought. What am I missing on this line? Does anyone see what I've omitted strategically, but I want to make the point that you should not do? Parentheses. Where do I need parentheses on this line? This is super important, so I don't want to lose this point. Where should I put parentheses on this line to make it an honest rendition of what came before it? What has actually been grouped together in this expression? The fractions. How?
Simplified the first two, or the second and the third one.
Okay.
So you can distribute into the first and the third one, so you distribute to the second and the fourth one.
Right. So before we were talking about jumping this 10 across and hitting all 4 of the terms that are in the numerators of those fractions. Why does that happen? Because the x minus 2 is all part of the same happy numerator family of that fraction. So that x minus 2 is grouped together by the fraction bar that's underneath it. Same thing with the 2x plus 1. It's being grouped together, those two terms, by the fraction bar that's underneath. So I need to make sure that that grouping is preserved. This is the error I saw I think every one of your groups make in the process of solving this equation. That x minus 2 still needs to be grouped together. That 2x plus 1 still needs to be grouped together, even after all the dust settles from the fraction multiplication that we just did. And having those parentheses in there makes a big, huge quantitative difference on the very next step that you're about to do. Because now, how do I get rid of these parentheses? Multiply. Multiply. Distribute the multiplication on the outside of them across the addition that's on the inside of them. Which in the first case gives me 2x minus 2 times 2, so 2x minus 4. In the second case, it gives me negative 5 times 2x, and it also gives me negative 5 times 1. So the mistake that every one of your groups made at one point in the solution of this equation showed up right there as a minus 5, which is what we want. But if you forget those parentheses weren't there, then the 2x will get multiplied by negative 5 and become negative 10x. But the 1 isn't going to get multiplied by negative 5. Instead, it might have gotten multiplied by positive 5, depending on how you did your grouping along the way. but we need that whatever happens to that 2x, the very same thing happens to that plus 1, because they're grouped together in the original fraction by that fraction bar. So if you had a plus 5 at this line, you were in good company. But that's not correct. That was, I think, we've made our way to the end of the real thorny part of this problem. So now if I want to get the x by itself, what should I do? What's my next step? Now that my fractions are gone. Let's simplify the left-hand side by combining like terms. I have 2x and negative 10x that are like terms because they have the same variable factor, x. So what is 2x minus 10x? Negative 8x. I also have another pair of like terms. Negative 4 and negative 5, the constants. If I get those two together, they make a negative 9. Then the right-hand side of the equation, 10x minus 7. So now I've simplified both sides of the equation to the extent possible. And now I'm ready to tackle the next problem, which was to get all the variable terms to one side by subtracting. What should I subtract from both sides of this equation to get all my x's to be on one side? What did you subtract here? I saw your papers. I know you did this. Let's subtract 10x. If I subtract 10x from the right-hand side, all my x's from the right-hand side will be gone. Right? They will cancel. And therefore, this is a helpful strategy, because afterwards, all my x's will be on the left. Negative 18x minus 9 equals negative 7. And now that all of my x's are on one side, all we have left to do is unwrap those x's by reversing the order of operations. If I'm reversing the order of operations on the left-hand side of my equation where I have both multiplication and subtraction happening, what should I undo first? What operation should I undo on the left side of this equation? Yeah, exactly. I want to undo first that which the order of operations does last. I want to undo the subtraction of 9 by adding 9 to both sides. Negative 7 plus 9 will give me positive 2. And finally, how do I get that x by itself? Divide by negative 18. And then reduce that fraction that we get. X is negative 2 over negative 18. What's a better way to write that fraction? Negative 1 over 9. Yeah, don't forget the 9 should be in the denominator with this x equals negative 1/9. So this problem had a whole lot going on. And if you take a Module 2 quiz today, you will see a problem that looks like this. This is maybe even slightly more going on in this one than the one that you might see on the module quiz. But it's still the very same strategy that we used on Monday for slightly simpler problems. First, clear all the denominators. Get all the fractions out of your life right away, multiplying by a common multiple of all the denominators. And if you navigate your way successfully through that process, and here we needed to remember the groupings of terms by the fraction bars mean that we need sets of parentheses in this process that were not obvious in the original equation. It might help whenever you have an equation like the one that we started with, before you start doing work on it, you might think about just adding in your own parentheses in these numerators to remind yourself that when you go to do this arithmetic later on, those began their life grouped together, and so they need to remain grouped together until all the simplifying is done. But then once the denominators are all cleared, we needed to move our variables from both sides of the equation over to one side of the equation, which we did by subtracting 10x here at the bottom. Then we had a simple equation with only whole number arithmetic going on and an x only on one side, and then we're ready to knock it out by reversing the order of operations.